Hello, we are here to talk about the beginning of chapter 10. We have two sections we're going to do in this chapter, and that wraps up the course. So today we're looking at correlation. So the main thing we're going to be looking at is a thing called the linear correlation coefficient, which is represented by the variable r. This is a number that measures how well paired sampled data fit a straight line pattern when graphed. We use the sample of paired data, sometimes called bivariate data, to find the value of r, and then we use r to decide whether there's a linear correlation between the two variables. We're only looking at linear relationships, so if you look at the data in a scatter plot, the points will approximate a straight line pattern. We're going to, after that, discuss methods for conducting a formal hypothesis test to decide whether there is a linear correlation between all population values for the two variables. So what is correlation? Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Very important, this does not mean that the values of one variable cause the values of the other variable to do something. It just means that there is a relationship between the two things. A linear correlation exists between two variables when there's a correlation and the plotted points of pairs of data result in a pattern that's approximated by a straight line. So looking at some scatter plots, you can see there is a linear correlation between x and y here. As x increases, y increases. This is called a positive correlation. I actually give you an R value for this one of 0.859. That's not super meaningful at the moment. Here's another one, negative correlation, negative 0.971. You can see that as the absolute value of that R gets closer to 1, these line up more into a line. These are a little more scattered. These are more lined up. This is a negative correlation because as x increases, y decreases. This scatter plot has a R value of very close to 0, and you can see it doesn't line up linearly. This looks like you just threw paint on a wall, basically. There's no distinct pattern, and you would believe that there's no correlation here. We'll have tests to decide when there is and isn't later on. There is a very distinct pattern on this graph, this plot, scatter plot, but the pattern is not a straight line, and there seems to be some sort of non-linear relationship going on. You probably recognize this as like a parabolic relationship. There is an R value of 0.3, so I'm not 100% sure what to make of that. So R values not only measure whether there is a correlation, but also the strength of that correlation. They can be positive, they can be negative. The closer to 0 that they are, the less strong the correlation is, and the closer to 1 or negative 1 that they are, the stronger that relationship is. Okay, one thing that we are not going to do is calculate this R value. There are a lot of symbols in here that I do want to talk about quickly. N, once again, now we're going to talk about is the number of pairs of sample data. So that's a little bit different. We're not counting up like doubling, right? We're just counting the number of pairs. So for every x, there's a y. This next symbol here is the summation symbol. Looks like a big E. The summation symbol denotes the addition of the items indicated. Sum of the x, you're adding all the x values. Sum of the x squared, adding all the x's squared. Sum of the x quantity squared, that means you add all the x's up and then square them. Sum of the xy, you multiply each x times y and then add all those. R is the linear correlation for coefficient for sample data, and P is the linear correlation coefficient for a population of paired data. We won't really get into that one very much. So I will just show you why we're not using the formula. Here is the formula for calculating R. It's n times the sum of the xy minus the sum of the x times the sum of the y divided by a big square root of n sum of the x squared minus sum of the x quantity squared times the square root of n times the sum of the y squared minus the sum of the y quantity squared. This is a ridiculous formula. I have worked a few of these out by hand in my time. It's not as awful as it appears, but there's also no reason to do it when you can get the R value from technology very, very quickly. So one of the things that they do is they kind of go through by hand calculations for these things. Again, we're not going to do that. At the end, you can get this R value, and you can also get a P value from technology, which is what we're going to do. And you can use that P value and compare to alphas, similarly as we have in the past, to evaluate claims about correlations. There's a table A6 that can be used to determine whether R values that you get are significant or not. Basically what you're looking for there is if R is greater than the value on that table, then you can support your claim that there is a linear correlation, and if R is less than that critical value, then there is not sufficient evidence to support the claim of a linear correlation. So some properties of the linear correlation coefficient: the value of R is between -1 and 1. If all values of either variable are converted to a different scale, the value of R does not change. So like if you multiplied them all by 100 or something, that wouldn't change the R value. The value of R is not affected by the choice of X or Y. You can interchange all the X and Y values and the value of R will not change. So it's a judgment of the strength of the relationship of these two things, and it doesn't matter which one's X or which one's Y. It's still just measuring how strong that relationship is. 4R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that's not linear. So that one that we had before that was parabolic, this is not doing a good job of measuring that. And R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value. So, example, finding R, you have this data, chocolate and Nobel. I have no idea what this data is supposed to mean, but you have 5, 6, 6, 9, 4, 3, 4, 2, and 5, 11. They show you how to do that on a TI-83 or 84, but we can also do it in StatCrunch. You go to Stat, Regression, Simple Linear, and then I've already got this data typed in my variable 1 and variable 2. I'm just going to leave this alone, these hypothesis tests that it's currently doing, and I'm going to go ahead and hit Compute. You can see my linear regression values that popped up here. There's a lot of information on here. You can see the correlation coefficient, though, is right there, 0.7949366. If we go back here, you see they found the same thing, 0.7949366, or 0.795. Now they go through the many steps of doing this with the formula. To eventually get the same thing, 0.795. But yeah, so that's it. It's really easy to calculate in StatCrunch. A more important question, is there a linear correlation? So this happens when you get your value. What does that mean? Is an R value of 0.2 good? Is an R value of 0.7 good? Is an R value of 0.8 good? The answer to that question lies in a table that is in your textbook. It's in Appendix 6, Table A6, and basically what this has got right here, it has an alpha of 0.05 and an alpha of 0.01. And you look up based on your number of pairs of data that you have. You look at the right alpha, and this gives you a critical value. And if your R value is greater than that critical value, then you can say that there is a linear correlation with this particular significance level. And if it's not, then you cannot say that. So for example, the one that they want us to look at is using an R value of 0.801 for 23 pairs of data, and using a significance level of 0.05, is there sufficient evidence to support a claim that there's a linear correlation between chocolate consumption and numbers of Nobel laureates? Well, now we know what that data means finally. Well, if you look for 23 pairs of data, that would be somewhere between 0.396 and 0.444 for a critical value at the 0.05 level, and actually 0.505 and 0.561 at the 0.01 level. Well, we're at 0.8. So yes, there's definitely significant evidence where we can support that claim. You can see that what is happening here is we were looking at the no correlation land would be somewhere between 0.396 and 0.444. There's a kind of complicated way to get the exact number from technology, or you could look it up online. There's many better, longer tables online that could do this. But anyway, we're at 0.801. That's way out here in the correlated area of this chart. The other way that you could do this, instead of using that table, is you could use technology again. I had to enter all this data here, but you could go do a regression, simple linear, variable 3 and variable 4, compute, and you look at the p-value of the model, and you can see that p-value is very, very low, less than 0.0001, so that this definitely is a very good correlation here. Okay. Interpreting R, explained variation. The value of R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. So that's why it always spits out the R squared value. So for example, using the 23 pairs of chocolate Nobel data, there's an R of 0.801. So if you square that, you get 0.642, and what that tells you is that 64.2% of the variation in numbers of Nobel laureates can be explained by the linear relationship between chocolate consumption and the number of Nobel laureates. So 36% of the variation of numbers in those laureates can't be explained by the rates of chocolate consumption. A couple more things here. Interpreting R with causation, don't go there. Correlation does not imply causality. So it is absurd to think that eating more chocolate would help win a Nobel Prize. So common errors that happen with this: assuming that correlation implies causality, using data that's based on averages, and ignoring the possibility of a nonlinear relationship, like, oh, look, that was clearly parabolic back there. We should have looked at that. The next thing down here is about formal hypothesis testing. You can do formal hypothesis testing on this stuff. I think this is actually a rho value, but we'll just call it a P. If you're conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, use the following null and alternative hypothesis tests. Use rho to represent the linear correlation coefficient of the population. So we're looking for the null hypothesis rho equals 0 versus the alternative that it's not. So basically we're saying there is no correlation or there is. You could do test statistics and all that stuff similar to how we did the test previously. But it's, again, easier to look at p-values. It is also possible to do a one-tailed test. If you just wanted to check for a negative or a positive correlation, you could also do that. Looking back at our data that we had here, if we look at either one of these regressions, let's go back and do the first one. It's already set up for hypothesis testing. And you can see that our p-value for our model is 0.108. So that is almost certainly, I mean, that's not within a 0.05 level or anything like that. So this is not a significant correlation that we're looking at here. We could not reject the null that these things were correlated. Whereas on the second one that we did, we already looked at this before. You go down and look at that p-value on the model, and you can see it's less than 0.0001. We can reject the null. These are correlated. Okay, I think that's where I'm going to stop on this video.